Hello students, this video is the review for the multiple choice questions from Chapter 5. If you recall, Chapter 5 was the probability chapter. It talked about flipping coins, drawing cards, and also developing probability distributions. The first thing I'm going to do is show you the correct answers for these multiple choice questions, including one that you probably are a little surprised about. So here's the answer key. You can see that all the questions from 1 to 23 are given here. That number 12, I asked you to skip. You do not have to do number 12. That's why I put LOL. Of course, that doesn't mean that answer is LOL. All right, I'm going to try to do all of the questions here, and I'm going to try to go as quickly as possible, so hang in there. Let's begin. You read in a book about bridge that the probability that each of the 4 players, so we know that we're dealing with 4 players, is dealt exactly one ace is about 0.11. That means that, okay, this question is not really talking about the number of players, not really talking about the number of aces. It's really talking about what probability means. And probability, as you recall, is not a promise. If I say that the probability of flipping a coin and landing on heads is 1 out of 2, that doesn't mean that every single time I flip a coin, it's going to, every 2 times I flip a coin, it's not going to land 1 heads, 1 tails, right? Probability is what's going to happen in the long run. So you got to be careful to look for the things that aren't promises, but is a description of what's going to happen in the long run. All right, so let's take a look. In every 100 bridge deals, each player has 1 ace exactly 11 times. This exactly is something we really want to shy away from in statistics. Nobody's ever promising you anything in statistics, so I'm not saying it's choice A. In 100 bridge deals, it's 11 times. Well, 11 over 100 is 0.11. However, that's not how it works. As you recall from doing simulations, if we do a simulation, sometimes it'll come up the way we expect, but sometimes it won't. In 1 million bridge deals, that's a sufficiently large number. The number of deals on which each player has 1 ace will be exactly, can't use exactly, it's not a promise. In a very large number of bridge deals, the percent of deals on which each player has 1 ace will be very close to 11%. That sounds about right. The percent of deals on which each player has 1 ace is very close, that's not a promise, to 11%. For letter D, in a very large number of bridge deals, the average number of aces in a hand will be very close to 0.11. This question isn't talking about the average number of aces. This is saying 1 ace. The probability of that happening in 4 players is 0.11. So that's not what this is talking about. This changed the thing that it was talking about. So we're not going to guess D. And since we already found the correct answer of choice C, obviously it's not going to be none of these. Moving on. If I toss a coin 5 times and the outcomes are tails, 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 a lot of tails, the probability that tails appears on the next toss is, remember, a chance process does not have a memory. If I give you a chance process and I say, well, what happens if a run of bad luck happens? It doesn't matter. A chance process is always going to have the same probability associated with it. 0.5 is for coins, right? If it was dice, if I rolled a fair die 1 billion times and it landed on 1 every single time, the next roll would still have a probability of 1 out of 6 to land on 1. So don't get fooled by memory, because chance processes do not have memory. I guess in that specific instance, if it was 1 billion times and always landed on 1, I would suspect the die to be weighted or something like that, but that's beyond the scope of this discussion. Exercises 3 to 5 refer to this basketball player makes 47% of her shots from the field, which, I don't know, is that good? Let me look that up. All right, here I am again to tell you that the percentage for field goals for this year and last year and the year before that is right around 0.46. 0.46 for 2019-2020, 0.461 for 2018-2019, and 0.460 for 2017-2018. So right around the correct average. Is actually a little bit better than average. Anyway, to simulate whether a shot hits or misses, you would assign random digits as follows. Now keep in mind, she makes 47% of her shots, which means she misses 53%. So we need to come up with a system that represents 47% of the time it's going to miss, 53% of the time it's going to hit. 1 digit simulates 1 shot. Instantly no good, because there's no way that I could represent 47% using 1 digit. Remember, 1 digit is only going to go up to from 0 to 9. That's only 10 different possibilities. So I could simulate 40% or 50%, but not 47%. Again, 1 digit simulates 1 shot. No good. See you later. And choice C is a very common distractor. You might think that is choice C. 2 digits simulate 1 shot. which makes sense. 00 to 47 are a hit. Oh, that's great. 47. That's got a 47 in it. Keep in mind we're starting at 00 though. If you're starting at 00, that's an extra number. That's not starting at 01. So 00 to 47, there are actually 48 different possibilities. Unfortunately, we're not talking about 48%. We're talking about 47%. So we got to cut that one off. 00 to 46, that is 47 different numbers. And 47 to 99, that's 53 numbers. Count it out. This one is the correct answer. And this one is just representing 00 to 45. That's 46 possibilities, and we're looking for 47%. That's what we're looking for. All right. Use the correct choice from the previous question, which is choice D. That's what we found from the previous question. And the random digits to simulate 10 shots. Okay, let's simulate those shots. First shot, 82. According to this, 47 to 99 is a miss. So that one is a miss. So I'm going to put a little tally mark in the miss section. 73, unfortunately for her, is another miss. And then the next number is 47. 47. Remember, in this scenario, 46 is a hit, but 47 is a miss. Next is 14. There's our first hit. Next is 90. There's a miss. Next is 20. Remember, 00 to 46 is a hit, so that one's a hit. The next one is 46. Another hit. What have we done so far? 4, 5, 6, 7. 74 is a miss. We'll hash that. 75 is a miss. 11 is a hit, and I think that's all she wrote, right? 4 plus 6 is equal to 10. So we did 10 shots. Nice work. How many of these 10 shots are hits? Looks like there are 4 hits. Not too difficult. All we had to do was literally do the math. You want to estimate the probability that the player makes 5 or more out of 10 shots. So you simulate 10 shots 25 times and you get the following number of hits. So we're trying to estimate the probability that the player makes 5 or more of 10 shots. That's what we're looking for in our results from the simulation. So how many of these are 5 or more shots? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So that means we've got 12 times in which the player makes 5 or more of 10 shots, divided by the total number of simulations. That's 25. So 12 over 25 is going to be our correct probability of the player making 5 or more of 10 shots. 12 out of 25 looks to me like it's choice C. So I'm going to circle that right now. Why didn't I choose any of these other ones? Come on, kid. 12 out of 25. All right, moving on to question number 6. 10% of U.S. households contain 5 or more people. Crowded house. You want to simulate choosing a household at random and recording whether or not it contains 5 or more people. Now keep in mind, it says 10%. That's our probability of, I guess, quote unquote, success. Which of these are correct assignments of digits for the simulation? All right, well, 10% of U.S. households. That means 10% of the time we're going to get 5 or more people. 90% of the time we're going to get fewer than 5 people, right? 4, 3, 2, 1, or 0. I guess household with 0 wouldn't really be a household. This one, the first one talks about odds and evens. That's a 50% chance. We're not going to do that one. The first one says 0 is yes and 1 through 9 is no. That seems to make sense to me, right? 0 is yes and 1 through 9 is no, because 1/10 of the time it's going to be yes and 9/10 of the time it's going to be no. So this one is correct. Is that the correct answer? Well, let's see. 5 is equal to yes. Oh, interesting. That's a 1 out of 10. And then 0 through 9 skipping 5 is a no. That's also true. Interesting. So we have to figure out what's going on here. The next choice says all 3 are correct. Well, we already know that A is incorrect, so let's cut that one off. So using process of elimination, it's probably either going to be B or C, right? Nope, it's going to be E, because E says choice B and choice C is correct, but A is not. Is that annoying for a multiple choice question? Yes. Is it something that you might see? Probably. All right, in government data, a household consists of all occupants of a dwelling unit. Yes, we're still on households. Choose an American household at random and count the number of people it contains. So right here, you can see a probability distribution. You can see the number of persons per household. If there's only one person in the house, it's a 25% chance of that happening. If there's 2 people in the household, it's a 32% chance of that happening, and so on. These question marks are the things that we don't know. But remember, in a probability distribution, it follows certain rules. And just as a quick reminder, here are the rules. All the probabilities have to be in between 0 and 1. And so far, that's correct, because all of these probabilities are positive decimals between 0 and 1. And the sum of the probabilities has to equal 1, which means all of these numbers together get up to 1. Great. It says the probability of finding 3 people in a household, oh, that's this one, is the same as the probability of finding 4 people. Oh, that's this one. Since we don't know it, we're going to assign it a variable, which in this case, I'm going to call it x. That makes me happy to do so because I'm a math teacher and that's my whole thing. The probabilities are marked with question marks in the table. The probability that a household contains 3 people must be, well, all we got to do is set up a scenario in which all of these numbers add together to give me 1. And here's that scenario. I have all of the numbers from the table plus 2 x's add up to equal 1. I think the main thing that students get wrong here is sometimes they'll just put 1x rather than 2. But I'm not going to show you how to solve this because this is not an algebra class. Easy to do. Solving this equation yields x equals 0.16, which means here is our answer. We're looking for the value of x, which is the probability that a household contains 3 people. In a table of random digits, such as table D, sometimes also referred to as table A, there are all sorts of tables, really. Each digit is equally likely to be any of these values. What's the probability that a digit is 7 or greater? Well, I know 7 or greater is either 7, 8, or 9. So that's 3 out of 10. Not sure why this was such a stumbling block for some students, maybe because sometimes students think of 0 as representing 10, but keep in mind 7 or greater, 7, 8, or 9. There's only 1, 2, 3 options. Moving on to question number 9. 20 of a sample of 275 students say they're vegetarians, so that's 20 out of 275. Of the vegetarians, 9 eat both fish and eggs, and 3 eat eggs but not fish, and 8 eat neither. Okay, so we have a lot of numbers floating around here. We could organize this into a table, but let's read the rest of the question. Choose one of the vegetarians at random. Okay, one of the vegetarians at random. That means all we're concerned about is the 20 vegetarians in the sample. We're not concerned about the rest of the 235 people because only 20 of them say that they're vegetarians. So that makes it a little bit easier. What's the probability that the chosen student eats neither fish nor eggs? Now we have something to go on. And if you'll remember from the class that we did Venn diagrams, this is probably the way that I'm going to use to answer it. A Venn diagram consists of 2 different bubbles, and the 2 different bubbles represent 2 different categories. In this case, the categories are going to be whether they eat fish, whether they eat eggs, whether they eat both, or whether they eat neither. And remember, in a Venn diagram, another aspect that you need is this rectangle that represents the universe, and this rectangle down here that represents neither. So let's label this diagram a little bit. All right, we got fish in this bubble, we got eggs in this bubble, and we got U, the universe, all of the different things in the set is equal to 20. Now, we are told that 9 of the vegetarians eat both fish and eggs. So that piece of information goes there. It does say 3 eat eggs, but not fish. And then it says 8 eat neither. Okay, so that means the 8 is going to go down here. Easy. One thing that I could figure out from this information is the students that do eat fish but don't eat eggs. So I got 9 and 3, that's 9, 10, 11, 12. I got 8, that actually ends up being 20. So the number of students that eat fish but not eggs turns out to be 0. All right, now that I have my setup here, I'm ready to answer the question. What's the probability that the chosen student eats neither fish nor eggs? Oh, well, it says 8 eat neither, right? So that was maybe a little bit more straightforward than was required. But it's a good thing that we set up the Venn diagram because now we know how to set up a Venn diagram. Neither fish nor eggs, that's 8 students out of 20 total. That's going to be choice C, 0.4. Not bad. Moving on along to rolling 2 dice in this casino game. What a very rude word. I'm not going to say that live on the air here. Here's the assignment of probabilities to the sum of the numbers. In order to get a 2, the probability of getting a 2 on 2 dice is 1 out of 36. The probability of getting a 7 is 6 out of 36. The probability of getting 11 is 2 out of 36. It's a nice little symmetrical probability distribution. I'd love to see that. The most common bet in this game is the pass line. The pass line wins immediately if it's either a 7 or an 11. So now what we're going to try to do is use the addition rule to combine the probabilities of these 2 things, of course, provided that they are mutually exclusive. So here's the general addition rule, which gives us A or B, 7 or 11, is going to be the probability of 7 plus the probability of 11 minus the probability of both of them happening at the same time. Well, remember, You can't have that when you have two mutually exclusive events, like the sum of two numbers giving us 7 and 11 at the same time. So now let's write down the specific addition rule for mutually exclusive events. And that just says that the probability of A or B is equal to the probability of A plus the probability of B. Let's add these together. We got 2 out of 36 plus 6 out of 36. That's 8 out of 36. Not too shabby. I notice that what we have here is a non-simplified fraction. The question that sometimes students ask is, when am I supposed to simplify the fraction? And if so, when? On a multiple choice question, you look at the choices, right? On a free response question, you can either simplify or not. That will not affect the value of your answer, whether it's partially correct, whether it's essentially correct, or whether it's incorrect. An athlete suspected of using steroids is given 2 tests. Oh my gosh, 2 tests in one day that operate independently of each other. It's important to know that they're independent because, well, you'll see why in a moment. Test A has a probability of 0.9. Test B has a probability of 0.8 of being positive, or being accurate, I guess you could say. What's the probability that neither test is positive if steroids have been used? All right, well, now let's figure out the probabilities of each of these independent things here. The probability of test A being neither test is positive. So A being negative is equal to, well, the probability of A being positive is 0.9. So that would be 1 minus 0.9. That's equal to 0.1. I just used a little rule called the complement rule. And similarly, the probability of B being negative, so the probability of B negative is equal to 1 minus 0.8. 0.8, that's equal to 0.2. So these are the probabilities that these individual tests will be negative. Now, what's the probability that neither test is positive? We got multiple events, so we're going to use the multiplication rule. And right here in red, you can see that this is the general multiplication rule, which always works for any 2 different events. However, in this case, we were told that these tests are independent, which means we can use the multiplication rule for independent events, which is slightly easier to do because that means we won't have to calculate this conditional probability. And this makes it a lot simpler because that means all we need to do is multiply 2 dumb numbers together. So we got 0.1 times 0.2. Guess what? That's 0.02. No big deal. Moving on to question number 12. Or are we? Remember, question number 12 was the one we were supposed to skip. Why did I just not delete this problem? Great question. Moving on to question number 13. Suppose a loaded die has the following probability model. Remember, a loaded die is, as alluded to before in the video, loaded means it doesn't have equal probabilities of each face landing. In history, people did what's called loading a die, which means putting more weight on a certain face. Sometimes, I guess in modern times, people use a microwave to do that. You can go ahead and look that up on YouTube. I'll let you do that by yourself. If this die is thrown and the top face shows an odd number, odd numbers, oh, how strange. Here's 1, here's 3, and here's 5. Those are the odds. What's the probability that the die shows a 1? Well, let's see. It's given to us that the top face shows an odd number. So this is a conditional probability. So remember, that means a condition is given or some information is given about the outcome, but not the total information, not all the information. So now, what is the probability that the die shows a 1? Let's try to write this out in probability notation. First, let's define our events. Let's let event A be the die shows a 1, and event B be top face shows an odd number. Now let's find the probability of each of these events. All right, the probability of A is 0.3. Well, wait, why isn't it 1 out of 6? Because it says the probability of getting a 1 is 0.3. It says it right here. And the probability of B, top face shows an odd number, is going to be 0.5. Why is that? Because it's 0.3 plus 0.1 plus 0.1. Excellent. All right, so that means we have the 2 probabilities here. We're asked the probability that the die shows a 1 if we know that the top face shows an odd number. So that's it written out into English. I find it useful to write it out in English first and then turn it into symbols. So die shows a 1, remember that's A, given that the top face shows an odd number, remember that's B. Here's how it looks in probability notation. All right, so what we're really calculating is the probability of A given B. Now, it turns out that all you need to do is refer back to the formula for conditional probability. Very easy to find. All we need to find is the probability of A and B happening at the same time. Divide that by the probability of B. In this case, the probability of A and B happening at the same time is very easy to figure out. Well, die shows a 1 and top face shows an odd number. The only overlap between those two things is if the outcome is actually 1, which has a probability of 0.3. So that probability is going to be equal to 0.3. Let me type that in here. And the last part of this is the denominator, which is probability of B. That's 0.5. And I took the liberty of calculating 0.3 divided by 0.5. That's 0.6. So our correct answer is 0.6. Let me get the marker here, not the highlighter. Here we go. Great. On to question 14. Dr. Stats plans to toss a fair coin 10,000 times because Dr. Stats is a cool dude that has lots of time on his hands, on the hope that would lead him to deeper understanding of the laws of probability. Which of the following statements is true? Remember, there are a lot of things we know about probability, like it doesn't have, chance processes don't have memories, and probability is not a promise. It's unlikely that Dr. Stats will get more than 5,000 heads. I don't think that's true. I think it's fairly likely that he'll get right around 5,000 heads. So I don't think it would be unlikely that he would get more or unlikely that he would get less. I think it's equally likely for both. So let's cross that one off. That one doesn't sound right. Whenever Dr. Stats gets a string of 15 tails in a row, it becomes more likely that the next toss will be head. Remember, probability is not a promise and chance processes don't have memory. Specifically, they don't have memory. That means we're not going to alter the probability of independent events because of what happened before. The fraction of tosses resulting in heads should be close to 1/2. Well, that seems to be pretty sensible, right? Because if you flip the coin 10,000 times, you could get 5,000 heads, or maybe like 4,500 heads, or like 4,799, or like 5,010 heads, but it's probably around 5,000. So it should be, ooh, I love that, should be close to 1/2. That's the front runner so far. For choice D, the chance that the 100th toss will be a head depends somewhat. What? It depends on the results of the first 99 tosses? No way. Memory is not a thing. All of the above statements are true. Get real. Choice C is our answer. For 15, China has 1.2 billion people. I think that this was written a little while ago. Almost certainly more people in China now. As a matter of fact, I just Googled it, and in 2019, I'm dating this video a little bit. In 2019, Google says that the Chinese population amounted to about 1.40 billion people. So this is a little outdated, but who cares? Marketers wanted to know which international brands they've heard of. A large study shows that 62% of all Chinese adults have heard of Coca-Cola, which means that 38% of Chinese adults have not. What we want to do is simulate choosing a Chinese person at random and asking if he or she has heard of Coca-Cola. One correct way to assign random digits to simulate the answer is, well, let's do another simulation. 62% of all Chinese adults have heard of Coca-Cola. 38% of Chinese adults have not heard of Coca-Cola. So I don't think that one digit is going to cut it here. Do you? Certainly not, because remember, we're not looking in increments of 10%, we're looking in increments of 1%. So we're looking for something with 2 digits in it. And we've come to this trickery again. Starting at 00 means, well, if I go from 00 to 61, that's 62 possibilities. If I go from 00 to 62, that means 63 possibilities. That's wrong. That's right. Choose an American household at random and record the number of vehicles they own. We're really talking about houses and cars and all sorts of very adult things. Here's the probability model, the probability distribution. A housing company builds houses with 2-car garages. What percent of households have more cars than the garage can hold? Well, 0 is going to work. 1 is going to work. 2 is going to work. But 3, 4, and 5, these households have 3 or more cars. That means they're not going to fit inside of the garage. So 0.13 plus 0.05 plus 0.02. And remember, these are independent events because you're not going to own 3 cars and simultaneously also own 4 cars. It doesn't make any sense. So 0.13, 0.05, and 0.02. Adding those together, what is that? 7 and 13, that's 20. So 20%. Moving on to the question about Alexa. Computer voice recognition software is getting better. 98% of all words spoken by a trained user, that's very good. I remember back in my day, I used to talk to my computer all the time, didn't listen to a word I said. Simulate recognizing a single word when the probability of being correct is 0.98. We're going to let 2 digits simulate 1 word. So 00 to 97, I remember this old trick, 00 to 97 means 98 possible choices, means correct. So the program recognizes words independently. So we're going to simulate using these random digits. The number of words recognized correctly out of the 10. We're going to do this simulation 10 times. And this time I'm going to do the over-under method. So here is the first simulation, 60. That is between 00 and 97. That means that is a success or correct, which means we get 1 tally mark under correct. Now I'm going to do the next one, which is 97. Remember, 97 is right on the cusp, but it still means correct. Perfect. 07 is going to mean another correct. And then 00 is going to mean another correct. Wow, we're not really going to get an incorrect unless the digit is either 98, 99, or 100. Maybe a little bit of foreshadowing. So we've done 4 already. Here's 24. Here's another correct. Here's 17. Another correct. Here's 86. Another correct. Here's 82. Another correct. Can he do it, folks? 98. Uh-oh. There's your incorrect. And then 43, the last and not least, that is 10 different trials, but 9 of them are correct and 1 of them is incorrect. That's how you simulate. Perfect. All right, we're in the home stretch. Moving on to question 18. And 18 to 20 refer to this GPA table. 1,000 students at a city high school were classified according to GPA, and whether or not they consistently skipped classes, as you could probably guess, there is a correlation between those things, but we're not going to talk about correlation in this chapter. Let's wait for chapter 12. What is the probability that a student has a GPA under 2.0? Well, let's see. Here's the under 2.0s. I got an 80 and I got 175. Looks like I'm going to add those two together and divide by the total. I don't have a total, which would usually be down here, but don't worry, I got you. We're able to calculate this column total. 80 and 175 together is 255, and that is our desired outcomes divided by the possible outcomes. There's 1,000 students. That's 0.255. We found our answer. It's right here. Here's the answer. What is the probability that the student has a GPA under 2.0 or has skipped many classes? Ooh, there's two different things going on here, and we got an or probability. Remember, or is going to happen when either of those two conditions are satisfied, but we have to be careful of the dreaded double count. So let's highlight the ones that we want. Student has a GPA under 2. That's these guys. Or gals. Student has skipped many classes. Skipped many classes, that's these folks. Okay? Looks like we have 175 and 80, and also 80, 25, and 5. So what we're going to do is add all of these things together, but subtract out any double counts. So there's 255 kids that have a GPA under 2.0. There's 110 kids that have skipped many classes. That is the column total and row total, respectively. However, we're looking for or, which means we can't double count. Looks like this 80 has been counted twice. So what we got to do is add these two numbers together. That's 365. And then subtract out 80 because we've counted it 2 times. And that means 255 plus 110, 365, minus 80 is 285. There is our correct answer. All right, moving on to question 20. What's the probability that a student has a GPA under 2.0 given, conditional, that he or she has skipped many classes? Okay, so now in order to do this, let's clear this chart a little bit. Now you could apply a formula to this. You could use the formula for conditional probability, but the way I prefer, especially if we have a two-way table, is to identify what it's talking about and only consider the students in that particular range. For example, the probability that a student has a GPA under 2.0, given this tells us all of the things that we're going to be considering for this problem, he or she has skipped many classes. So only the folks that have skipped many classes are going to be concerning me so far. Here's all the manys. That's it. Those are all of the kids that I care about. That means I don't care about any of the other kids. I know, sounds harsh. But anyway, he or she has skipped many classes. Well, that's 80, 25, and 5. That's 80 plus 30 is 110. Our new universe, our new, all of the numbers that we're considering is 110. So the probability is going to be something over 110. We're looking for the probability that a student has a GPA under 2.0. Well, among these folks, the folks that have a GPA under 2.0, there's 80 of them. So this number becomes 80. Go ahead, let me do it. Perfect. So 80 over 110. All we got to do is pop this in the old calculator and figure it out. Well, I mean, I guess we could do a little bit of game theory here. We know that 80 over 110 is bigger than half, so it's not going to be that, it's not going to be that, and it's not going to be that. Look at us. It's either going to be 80, which is probably not the correct answer. That's way less than half, or 0.727. Verify that on the calculator. I dare you. I'm telling you it's the right answer. For events A and B that are related to the same chance process, which of the following statements is true? All right, this question is probably the question that caused students the most heartbreak in years past. So let's focus on this pretty carefully. Let's first talk about the difference between independence and mutually exclusive, because they sound kind of similar and sometimes students lump them together, but they are in fact two different things. Remember that if two events are independent, that means that the probability of A and B is equal to the probability of A times the probability of B. Let's say that the two events are independent. In that case, they can't be mutually exclusive as well, because if they were mutually exclusive, this value would be the value of the probability of A and B, which means I can rewrite my equation like this. I want you to see how this equation doesn't really make sense, because consider these two events, the probability of A and the probability of B. These events are actual events, which means they have some outcomes. However, the zero product property says that if two numbers multiply together to give us 0, that means either one or both of these numbers also have to be 0. Since we're considering these events related to a chance process, since we're considering these events to actually be events that actually have outcomes, that means we can't have this situation occurring. So, if two events are independent, following this rule, that means they cannot be mutually exclusive, because if they were, that means one of those events would have to be equal to 0. Hopefully that makes sense, because that's probably the best that I've ever described it in my entire life. All right, choosing an American adult at random, the probability that you choose a woman is 0.52. The probability that the person you choose has never been married is 0.25. So we have two different probabilities with two different events. The probability that you choose a woman who has never married is 0.11. The probability that the person you choose is either a woman or has never married or both is therefore about, that means we have to combine these probabilities in some way. And the way you should start thinking about this problem is by using a two-way table. You could use a Venn diagram, but I already drew one, so let's think about two-way tables for a moment. I set it up as either woman or the complement of woman, and either married or the complement of married. I'm sure you could figure out the alternatives. All right, so it says the probability that you choose a woman is 0.52, so that goes down here. The probability that the person you choose has never married is 0.25, which means never married should go over here. These two values are column totals and row totals. Another way that we can refer to these as marginal probabilities. This is the marginal probability of choosing a woman, marginal probability of choosing a person that has never been married. Next, the probability that you choose a woman who has never been married. This is not marginal, but this is joint probability, the probability of two things happening, women and never married. That's 0.11. So that goes here. And again, we're calling that a joint probability because it's the joining of these two different events. What's the probability that the person you choose is either a woman or has never been married? Well, let's see. We can fill out the rest of the cells in this table by simply finding the other joint probabilities. For example, 0.52 is equal to 0.11 plus something else up here, which we can find very easily by subtraction. We can similarly find this joint probability, which is not a woman and also never married. Now, in order to find this other stuff, we need either this marginal probability or this marginal probability, but don't worry because the way the probability works is all of the marginal probabilities have to add up to 1. So 0.52, this becomes 0.48. And similarly, this marginal probability becomes 0.75 because they both have to add up to 1. So that means either I could subtract backwards this way or subtract backwards this way. I'm going to be able to get the probability that the person is a woman who is not a woman but who has been married pretty easily. All right, folks, I think we're finally ready to try to answer this question. The probability that the person you choose is either, that means we're using an or probability, a woman, that's all of these folks, and this one too, or has never been married. So that's the folks in never been married, that's here. All I got to do is add these three numbers together in the probability distribution. In the two-way table. I could add 52 plus 0.25 and then subtract out the double counts, but in this case I could just add together 0.41, 0.11, and 0.14. That looks like it's 4, 5, 6, it's a 6 at the end, and 4, 5, 6, it's a 6 at the front. So 0.66 is our answer. But of course, if you're more of a formulas guy, here's the formula and here's the answer. Notice I still got 0.66. All right, question 23. A deck of playing cards has 52 cards. Oh, big surprise. Of which 12 are face cards. We call those face cards the kings, the queens, and the jacks. If you shuffle the deck well enough and turn over the top 3 cards one after the other, what's the probability that all 3 are face cards? Well, we know that we're flipping these cards over without replacement, so that means the probability is going to change. These are dependent probabilities, and we can figure it out by simply doing the probabilities or writing out the probabilities by hand. It tells us that there's 12 face cards in the deck and 52 cards total, so it's a fairly simple, straightforward probability for the first card being a face card. But after that, the probability that the second card is a face card is going to be different because there's one less face card in the deck and one fewer card in the deck. And last but not least, my third card is going to have a different probability based on the fact that there's, again, one fewer face and one fewer card total. Now what we've done is figured out all the probabilities of these different events happening, and we've satisfied the condition of identifying the fact that they are dependent events, but we've calculated their exact probabilities. So we're okay to multiply these together now. So 12 out of 52 times 11 out of 51 times 10 out of 50. Here's what that looks like calculated out. And 0.009, be careful, this is the last stumbling block that students may face. 0.009 means I could round it to 0.01, not 0.001. There's our correct answer. All right, folks, that was the video on the Chapter 5 multiple choice review. Hopefully that was useful to you. Good luck studying.